Okay, hi everyone, welcome back. This is the third video for the fifth week when we will be discussing small world networks and the property of small worldness. In the previous video I already asked you to look at the documentary about two papers around the year 2000 that deal with small world and scale-free networks. Hope you have done that, and if you haven't, maybe pause the video now and first look at the documentary so things will go a bit quicker. To make a short introduction into the small world networks, when we measured properties of different real-world networks, and also people around the year 2000 started doing that, they realized that they have some intriguing properties like high clustering coefficient and also short path lengths, short distances between the nodes in a network. And then people look at different regular graphs and regular lattices and random graphs and so, and realize that none of these simple models have the same properties as real networks. In particular, the coexistence of high clustering and short distances between the nodes was not realized by any of the models. It turns out that it's not hard to get one of these two properties. For instance, high clustering, you can easily make a regular triangular lattice which has a lot of triangles, so also clustering coefficient will be high. But it turns out that lattices have long lengths between the nodes in the network. On the other hand, you can take a random graph where we prove that the distances between the nodes scale logarithmically with the size of the network, and logarithm is a very slowly increasing function, so distances will be short. However, we also prove that the clustering coefficient in a random graph would be close to zero, several orders of magnitude lower than what we see in real networks. So, small world networks are networks that have high clustering and short distances. And until the year 2000, nobody actually knew that it is possible to have a graph or a network with both of these two properties. Only when they start looking at real networks and realize that they have both of these two properties, the people started to think about how to get both of these two properties into one network. Okay, so let me move to the slides. This slide is again about the documentary. So our first real slide is about this small world phenomena that I just tried to explain. For instance, if you take a regular lattice, it's not hard to create a lattice with high clustering coefficient, but it's hard to create a lattice that would at the same time also have short distances between the nodes. It turns out that the distances between the nodes in lattices scale as n to the power of 1 over d, where d is the dimension of the lattice. So, one-dimensional lattice will be simply a chain, two-dimensional lattice will be a grid, and so on and so forth. So, according to the formula, the distances in one-dimensional lattice scale linearly with the size of the lattice. Distances in two-dimensional lattice scale as square root of the number of nodes. However, in real networks and also random graphs, we see that the distances scale logarithmically with the number of nodes. So, to talk about random graphs, we have shown that they have low clustering, so they do not reproduce this property of real networks. However, we do get short distances. And real small world networks have high clustering and also short distances between the nodes, as written down on the slide. And as an example, remember that in the case of Facebook from the year 2012, the average distance between the nodes were 4.7, and the corresponding value for a random graph, so the estimate for the random graph will also be around 4, so we also get short paths in random graphs. However, we don't get high clustering coefficient, so if you remember, in Facebook the clustering was 0.6. However, in a random graph, the clustering coefficient will be approximately the density of the graph, and so that parameter p in the Erdos-Renyi model, if you remember, and we know that real networks are sparse, so their density is super low. In the case of Facebook, density is smaller than 10 to the power of -6, so it's 6 orders of magnitude, or actually 5 orders of magnitude lower than in the real network. So in order to understand how it's possible to have high clustering and also short distances, we will again use a model which is simply called a small world model, and was introduced by Watts and Strogatz in '98, and probably this is one of the papers that started modern network science. So the model basically starts with the ring lattice that has a lot of triangles, so it has high clustering coefficient. But since it is a lattice, the distances are very long. And what the model does then is it randomly rewires the edges of this, or links of this lattice, and in order to make the distances between the nodes shorter. So it's basically creating shortcuts between different parts of the lattice. If, as you can imagine, if we would randomly rewire all of the links in a network, we will simply get a random graph, an Erdos-Renyi random graph, which has small short distances, but also very low clustering. But somewhere in between those two regimes of regular ring lattice and a random graph, there is a sweet spot where you get coexistence of short paths and high clustering. So let me draw the model on the blackboard and explain a couple of things, and then we will move back to the slides. Okay. So the model starts with a ring lattice, which with n nodes. So imagine we have n nodes positioned on a ring, and let's say that k, each node connects to k of the nearest neighbors. For instance, in the graph that I have just drawn, then each node connects to 2 of the nearest neighbors. Let's make that every node will connect to 4 nearest neighbors, so the parameter k on the slide will equal 4. So I should create a link here, and a link here, and another one here, and so on and so forth. So now we have a regular ring lattice where everybody connects to 4 nearest neighbors. At this point, the distances are relatively long, but the clustering coefficient is high because each link that I draw basically creates a triangle. On the slide, there is a formula to compute the clustering coefficient of this ring lattice, and the formula is derived as follows. So remember, the network clustering coefficient is defined as 3 times the number of triangles divided by the number of connected triplets. So let us first compute how many connected triplets there is in a network. Each connected triplet, like basically a path with two links, has one central node. And let this be our central node. So how many triplets are there where this node, or this black node, is the central node? Basically, since the node connects to k nearest neighbors, k over 2 to the left and k over 2 to the right, it basically all comes down to in how many ways I can randomly select two of the neighbors of the black node, which will basically give me the number of connected triplets where black node is the central node. The only thing is that I'm not allowed to go too far from the black node because there will be no links. Every node connects to only k nearest neighbors. So if you think about this, it's basically the number of connected triplets is the number of ways you can select two neighbors out of the neighborhood of black node. Since black node has k neighbors, the number of triplets centered in the black node will be simply k over 2. And since now we have only counted the connected triplets centered in this node, overall there are n nodes, so the final result is n times k over 2. Now let's also count the number of triangles that exist in this network. So I will copy this three. Again, I will start with one particular node and count the number of triangles of that node. So I will again get n here. Now let's also count the triangles. Imagine when I am counting the triangles, all the triangles look the same. So you start at some node, let's say black node, and you do 2 steps and then a step back. So you traverse 3 links and that will be a triangle. The only thing is that you are not allowed to go too far because you must have a link back to the black node in order to close the triangle. So if we count the number of triangles where their leftmost node is the black one, will be simply how far can I go from the black node in order that there will still be a link back. Since black node has k over 2 neighbors on the right hand side, this will simply be k over 2 over 2. And this is the formula that is on the slide. Now you have to simplify it and you will get exactly the formula listed there. And the final result that we get is 3 times k minus 2 divided 4 times k minus 1. So in our particular case, where k equals 4, what do we get? We get 6 divided by 12, so we get 0.5. The clustering coefficient is high, is 0.5. But as I said, we have long distances between the nodes. However, when we are randomly rewiring some of the links, meaning that I take a link and I randomly change one of its endpoints, or equivalently take the link out and basically put it back at some random location. At the very end of this process, if I rewire all of the links, I will simply be getting a random graph that has short distances. But it turns out that when you do this rewiring, somewhere in the middle it happens that you will get high clustering and short distances. And you can imagine that you're not allowed to rewire a lot of links in order to keep the clustering high, in order for our graph still to look like a ring lattice, but just you should just rewire enough links to make the distances very short. Here, what is this plot showing is the green dots are showing you the clustering coefficient during this rewiring process, and the purple dots are showing you the distances between the nodes during the rewiring process. And clustering and distances are both divided by the value of the ring lattice, just to have the vertical axis be between 0 and 1 for both of the measures. And notice that when you are rewiring the links, for some time the clustering still remains high. However, the distances start to drop dramatically. And after you, for instance, rewire 1% of the links, the clustering is still high. However, the distances are already super short, meaning that the distances decrease before the clustering drops. And in this regime that I'm trying to show you with my mouse, this is the sweet spot that I was mentioning. So you have high clustering and short distances. And notice also that this horizontal axis is logarithmic. So you don't rewire a lot of links. You just rewire a small fraction of the links. So a few links are no longer local, but become some shortcuts between different parts of the networks, and this already makes the world small. So this is the so-called small world model. As it says on the slide, this model is not practically applicable. I mean, Facebook did not start as some ring lattice and then people start rewiring the links. The only thing that this model tries to do is to explain that it is possible to have high clustering and short distances in one single network. Turns out that all you need is a few shortcuts. So I hope that you understood that. Otherwise, please ask on Piazza. To go to the next slide, here we are seeing the properties of few real networks that are all small world networks. And for each of the networks, you're seeing the number of nodes, the clustering coefficient, which is in most cases several orders of magnitude higher than what you would expect in a random graph. So notice when networks become large enough, the clustering coefficient is close to 0 in a random graph. On the other hand, I'm also showing you here the distances between the nodes that are relatively short, as predicted by the random graph model. To reiterate, what small world networks mean is high clustering and short distances. By high clustering, I mean usually several orders of magnitude higher what you would expect in the random graph. And short distances, by this I mean that the distances are comparable, at least according to orders of magnitude, to what you would get in a random graph. Be careful about some of the literature that treats small worldness, so small world networks, only as networks that have short distances. And that because the name small world implies that. However, as we learned, it's not hard to get short distances, it's hard to get also high clustering coefficient at the same time. So to move on, here I am listing 3 papers that in a way try to measure this small worldness or distances between the nodes in a network. And the so-called experiments of small worldness. The first one is the most famous one, Milgram's experiment from the 60s, where he asked random people from Omaha, Nebraska to forward a letter to some stockbroker in Boston. So they were simply, the only task was, here is a letter, forward this letter to that stockbroker. But you were not allowed to forward the letter to the stockbroker immediately. You are only allowed to forward or send the letter to a person that you know on the first name basis, so a friend of yours or something like that. In that way, you are traversing your social, this letter is traversing your social network. And here is a picture kind of showing how most of these letters reach their target. So notice that mostly the letters did one big step at the beginning, and then the steps became shorter and shorter until they reached the stockbroker. Most of the letters that actually came to the end, that the stockbroker actually received, on average took 6.2 steps. And this is where, so the average distance in the social network of people was estimated to 6.2, and this is where the term 6 degrees of separation comes from. The problem with this experiment, or before I go that, maybe a few other things that people learn when doing this experiment. For instance, the first few steps usually follow geographical location. People try to forward the letter as close as possible to Boston. Whereas when the letters came relatively close to Boston, people try to forward them based on the profession of the target node. They knew that node was a stockbroker, so at the end people usually try to forward a letter to some other stockbroker that they knew on the first name basis, hopefully that he knows the target stockbroker and he will be able, or she, forward the letter to him in the next step. The experiment also highlighted some tunneling effect at the end. So most of the letters at the last step went through one particular other stockbroker that then forwarded the letters to the target one. The problem with this experiment, so I will now make the camera larger. The problem with this experiment was that obviously most of the letters did not reach their target. I believe that around maybe 10% of the letters actually arrived to the stockbroker. And the reason for that was that people were simply not interested in to participate, or so they did not forward the letter, or the letters got lost, and so on and so forth. So, in a way, this value, 6 degrees of separation, is to some extent biased. Why it is biased? Because it's more likely that shorter paths succeed compared to longer paths. So imagine that there exists a path of length 3 from our starting point to our target point. And let's say that let P denote some probability that people will forward the letter due to some whatever reason. So the letter will be forwarded with probability P here, with probability here, and here. So the final probability that the letter will reach its target will be P to the power of 3. Now imagine a path of length 4. With the same reasoning, the probability that that kind of letter, so this starting point and this target point, where the shortest distance, the shortest path is of length 4, in order that this path will succeed, can be computed at P to the power of 4. And since P is relatively low probability, it's much more likely that shorter paths will succeed compared to longer paths. So in a way, the value 6.2 is biased. We would expect that the value is actually a bit higher because longer paths were less likely to reach the target, so the letter got lost, you cannot track that path, and you don't know its length. If we go back to the slides, you can see the second bullet here, which was the first time when people reproduced this experiment, but in this case they didn't do it with regular mail and sending it by post. They were actually forwarding emails from one person to another, and again you were only allowed to forward the email to somebody you know on the first name basis, because otherwise you could just Google the name of the guy, get his email and just forward it there, but that you wouldn't learn anything from that. And what was the key idea with email forwarding is that every time when some of the people on the way forwarded the email, they also sent an email to the designers of the study. So when chains were broken, meaning that emails were no longer forwarded or so, the designers knew at what point the email stopped, and they could then estimate what is the probability that an email will be forwarded after 3 steps, after 4 steps, after 5 steps, and so on. And based on this information, you can actually correct for the fact that longer paths are less likely to succeed compared to shorter paths. So if we look at the results, the result that they got was that on average these emails took 4 steps. So getting, calling it so-called 4 degrees of separation. When they corrected for the fact that most of the emails again got lost, they came to the value of 7, which is of course higher, but it's still a small number. So we're still saying that the world is small. And the final bullet here is just saying that on Facebook, the average distance in 2012 was 4.7, which they called 4 degrees of separation, which would actually be 5 degrees of separation, as we already discussed in class. So these are probably the most famous small world experiments that were reported in the literature. If we move on, we only have 2 more slides. So the question on this slide says, does existence of short paths imply navigable small world by decentralized search? Now let me again make the camera larger and what I mean by that. All these experiments so far, the model, the measures that we did, only tell us that there are short paths between the people in a social network, for instance, but say nothing about that, whether we are able to find them. So imagine I give you some letter or some piece of information that you are again trying to forward to, for instance, some stockbroker in Boston. If you would have the entire social network, you could simply run breadth first search from your node, or do Dijkstra algorithm if the network is weighted, find the shortest paths, and then try to forward them according to the shortest paths. But in practice, this is not realistic, because we don't know our social network. All we know is this node is me, and I am aware of my neighbors, my immediate friends. Maybe I also know friends of friends, but this is where things stop. I only am aware of my local neighborhood in a network. So the question is, how am I able, using just this local information, am I able to forward the letter to the stockbroker in very few steps? The same question would be if you are designing a routing protocol on the internet, where you have to route a package towards its final destination. You don't have the entire internet network, because it would be hard to store, it's commonly changing and so on. All the nodes are only aware of their immediate neighborhood. And still they have to make a decision to which neighbor to forward the package. And this, if I go back to the slide, this is what I mean by the word decentralized search. So that you're able to find short paths without having the knowledge of the entire network. So the question remains, does the mere existence of short paths, is that enough for us to do this decentralized search efficiently, to navigate through the network efficiently, or is there something else to it? And this is what people call navigable small worlds. So not only that short paths exist, but that they also allow quick navigation through the network. And it turns out that, for instance, the model that we discussed before, Watson-Strogatz model, it's not navigable. Short paths exist, but you cannot find them efficiently with decentralized search. However, real networks, many experiments show that real networks are in fact navigable. And you can look in this paper here that introduces a simple model again of navigable small worlds in which you are able to navigate efficiently using decentralized search. And it turns out that the key idea is that the number of neighbors that you have on some particular distance must scale with some particular function. So just as an example, for instance, that you have 4 friends that are close to you, and then 2 friends that are a bit farther away, and 1 friend that is even farther away, and so on. This geographical distance between linked nodes must actually follow some particular curve for the small world to be navigable. So if you're interested, maybe look at this paper. And going on to the final slide, which shows a historical development of small world networks, the theorem, the models, and so on. Here is the Stanley Milgram's experiment in '67. Actually, as you can read here, small world networks were actually people found out about them even before. This theorem, 6 degrees of separation, this is not something that Milgram came up with, but was actually first used in some Broadway play in the 90s, and people just took up this theorem. Then here are Duncan Watts and Steven Strogatz that published the small world paper about the small world model in the year '98. And finally, the Facebook data team estimated that the distances between the nodes on Facebook, the average distance is around 4.7. So this is it, what I try to say about small world networks. So once again, this is coexistence of clustering coefficient and short paths between the nodes. And again, be careful. For instance, in the Barabashi's book, he will be saying that the network is small world as long as it has short paths, which is not correct. We get that in a random graph as well. You also need to have high clustering. So that's it. I will pause here again, and the next video will be about your course projects. Thank you for listening.